to this. So this is aryl substituted cyclopropane is formed. Okay, right? Cyclopropane is formed from this compound. Okay. Next one, oxo-dipymethane rearrangement. So here the conditions of this compound of this arrangement are a photochemical reaction. This is a photochemical reaction of a beta gamma unsaturated ketone, to form a cyclopropane derivatives. Okay, that is first one. And next one is, so the main one is beta gamma unsaturated ketone. And next, formally accounts for 1, 2 acyl shift. 1, 2 acyl shift. And N2 pi star transition takes place in this. N2 pi star transition takes place. So, in dipymethane rearrangement, pi to pi star transition takes place, whereas in oxo-dipymethane rearrangement, N2 pi star transition takes place. And next characteristics is 1, 2 acyl shift is done in oxo-dipymethane rearrangement. Okay. So here again the products are cyclopropane derivatives. So that means, so 2 pi bonds are separated by sp3 carbon again, but it consists of an oxygen. So here this is alpha, beta, gamma, a beta gamma unsaturated ketone, right? So when light is absorbed by the compound and N2 pi star transition takes place, then substituted cyclopropane derivatives are formed like this way. Okay. So mechanism. So just take an example. First take an example. R, C, R, CH, double bond, CH2, CO, CH3. So this is our compound. And when light is absorbed by the compound, N2 pi star transition takes place. Then CH2, R, CH, CO, CH3 is formed. Okay. Substituted cyclopropane derivatives are formed. Right. So let us explain the mechanism. So first of all, take our alkene, that is a ketone, that is R, C, R, CH, double bond, CH2, C double bond O, CH3. So give the numbering to the carbon atoms 1, 2, 3, 4, 5. Okay, when light is absorbed by the compound and N2 pi star transition takes place, it undergoes singlet state. By intersystem crossing, it is converted into triplet state, and then so it divides into radical. Okay, at this case. So that is CH3, C double bond O, radical, plus R, C, R, CH, double bond CH2, radical. This is allyl radical. and this is acyl radical. Okay, that is the first step in the mechanism. And second one is acyl shift. So the main important characteristics of oxa dipi methane rearrangement is 1 comma 2 acyl shift, right? So that is how it is formed. Let us explain. So C double bond O, CH3, it consists of a radical CH double bond CH2 C R R. So it consists of radical here, right? So when this radical is attached to this carbon, then this electron shifted towards this carbon atom. Then C H single bond CH2 C R R. Okay. So the radicals are present here. Next, a bond is present here. Next, you can, in short, you can write as COCH. So then, so if you observe this, so this is actually the COCH3 is present at this carbon atom. Now it is shifted to this carbon atom, isn't it or not? So that means CH COCH3 C R R CH2 like this. Okay, so this is formed by 1 to Si shift. So this is the mechanism behind it. Okay, RCCH2 CHCO CH3. So like this way, oxa dipi methane rearrangement is observed. And we can take another example also. So this is when light radiation is in the presence of histophenol. Double bond one, then join this, right? So this is the product form here. This is another example. Another example. So this is our. So again alpha, beta, gamma. Beta, gamma unsaturation is there and keto group is present. So that's why we can apply oxa dipi methane rearrangement to it. Substituted cyclopropane performer. So the mechanism is hydrogen, light radiations again. We can next O, two radical. O, bond, bond. C2, C3 bond, C2, C3 bond breaks. That is 1, 2, 3, 4, 5. C2, C3 cleavage takes place. And two radicals are generated here. Next, these two form a bond. Consider a hydrogen like this. Join these two. Okay. So this is same as this one, right? So this is another example of oxa dipi methane rearrangement with mechanism. Okay. And next type is